Bismillahirrahmanirrahim. Assalamu alaikum, students. We are now starting the third lecture for week number our course of computer systems. In our last lectures, we have talked about mathematical representation of both frequency modulation as well as phase modulation. And we have discussed both time domain representation as well as the frequency domain representation of both modulation schemes. In our today's lecture, we will be talking about different circuits and hardwares that we use to generate and detect FM and PM transmission. So basically, we'll be talking about FM transmitters and receivers in this discussion. Although we should realize that FM and PM, they are interrelated, so both the schemes they can be generated in same fashion. So for today's discussion, we'll be mostly focusing on frequency modulation, but you should realize that phase modulation is also generated in same way. One important thing that we have previously discussed is that both FM and PM, they have constant envelopes. And having constant envelope gives certain advantages regarding the physical implementation or circuits and systems that are used for generating and detecting FM and PM signals. So in comparison to linear modulation schemes, they are rather easier to implement in certain cases. And moreover, because these are non-linear modulation schemes, so we can use non-linear modulation. We can use non-linear amplifiers in FM, which are practically more efficient as compared to the linear amplifiers. So this gives another advantage when we use FM for transmission purposes. So one thing that you should realize is that because for FM and PM, in both cases we are actually modulating the angle, so either frequency is changing or the phase is changing, and we want phase or frequency to change linearly with the message waveform. So these schemes, they require a linear relationship between message waveform and the phase or frequency of the sinusoidal carrier. However, these such devices, they are practically harder to obtain, but we can obtain this relationship for suitable band of operation, suitable range of frequencies. So it may not be possible to have a linear relationship over a wide operating range. However, for practical purposes, we can generate reasonably good waveform relating to FM and PM signals. So as I mentioned that we will be talking mainly related to FM. So FM can be generated by two methods. One is called direct method or indirect method. In direct method, we actually try to generate a sinusoidal carrier through an oscillator. However, the frequency of that sinusoid is changed by applying input voltage. So this is generally called voltage controlled oscillator, so which actually generates the frequency depending on the input voltage. In indirect method, FM is generated by using phase modulation. So first we generate a PM signal and then we try to increase its frequency deviation. We try to increase its frequency deviation in order to get the desired FM signal. So let us talk about the direct FM modulator. So as I mentioned, that direct FM modulator is basically generated by using voltage controlled oscillator. So what is a voltage controlled oscillator? This is basically an oscillator, as the name says, but the main thing regarding this oscillator is that its frequency is not fixed. So its frequency is dependent on the input voltage. So if input voltage is increased, the frequency of the VCO or voltage controlled oscillator gets increased, If frequency is decreased, the frequency generated by the VCO is decreased. So this is what we actually need from point of view of FM transmitter. So I have illustrated one implementation of a voltage controlled oscillator, which incorporates a varactor, which is actually variable reactor, with short form of variable reactor. So this is actually, you can take it as a variable capacitor whose capacitance change in accordance with the applied input voltage waveform. So since the capacitance is changing, so oscillator is also changing the frequency which comes out from this oscillator. So by using this varactor diode, which has a variable reactance, we can control the frequency of this oscillator waveform, which is by changing the input voltage. The good thing regarding this varactor diode is that this VCO based FM generation is that we can get a large frequency deviations directly by using the appropriate values of these different components. And secondly, this varactor diode, it has very simple implementation. However, it has a certain problem which is related to carrier stabilization. Sometimes the carrier frequency tries to drift off its free-running frequency, which actually creates problem in the frequency in the FM transmission. In order to overcome that problem, generally we now use integrated circuit based VCOs. So now we are more concerned, we are more focused towards IC based voltage controlled oscillators that can generate the FM signals directly in response to the input voltage. Although there are different integrated circuits developed by different manufacturers that can be used to generate FM signal, I have just represented one of the implementation, which is actually an IC MC1376 based VCO manufactured by Motorola. So this IC incorporates one VCO as an integrated circuits, and depending on the configuration of other components, it can generate an FM signal in response to the input voltage which is applied at pin number 5 of this IC. The input voltage is here XT, and the output is transmitted through an antenna. So basically the direct generation of FM is obtained by using voltage controlled oscillators, VCOs, that can be based on simple semiconductor variations, and all it can be fabricated using integrated circuits as just discussed. Secondly, we can generate indirect FM can be generated indirectly as well. The main idea regarding the indirect generation of FM is that we first generate a phase modulator signal with a relatively small frequency deviation, because we know that the phase modulation it can have only a small variation. So first what we do, we need to have a phase modulated signal which generates an FM signal through integration of integration. If you recall the mathematical forms of the FM and PM, you should compare those mathematical form. In the mathematical form of frequency modulator, we notice that the phase appears as the integral of the message signal. So you can see that the same thing is implemented here. Before applying to a phase modulator, we have integrated the message signal. So xt is a message. We have applied that message to an integrator, and then the integrated message signal has been modulated using a phase modulator. And that phase modulator of course would generate some modulated signal, but that signal would have small frequency deviation and a smaller center frequency, and for transmission purposes we need to have a larger frequency deviation and a larger larger carrier frequency. In order to do that, we generally pass it through a frequency multiplier that we have discussed in our last lecture as well, that there are certain circuits which perform as frequency multipliers. So we can use a frequency multiplier in order to increase the carrier the center frequency as well as the frequency deviation. Further, if we need to adjust the carrier frequency without changing the frequency deviation, we need to use heterodyning, as we discussed in our last lecture as well, and for that we sometimes incorporate a local oscillator LO of appropriate frequency in order to adjust the carrier frequency, and then the resultant FM signal, which is obtained after this frequency multiplication and heterodyning, it is amplified and transmitted over specific channel. So for this case, you would see that the entire frequency, if we look at this F1 signal, which is actually the phase modulated signal, the phase modulated signal would be represented by this. It will have some factor of a constant factor of t, and this phi delta represents the maximum deviation when it passes, maximum phase deviation when it passes through the frequency multiplier. You would see that the overall frequency would be multiplied by this factor n, because we have used the multiplication factor of n. So you would see the overall frequency to be this value, and you can see that this entire thing n pi delta upon 2 pi t, this can be treated as this f delta or frequency deviation, and the carrier frequency would be this n into c1, and which can be further adjusted by using a local oscillator. So overall carrier frequency would be represented by nfc1 minus flo. So this is how we can generate FM signal indirectly by using phase modulation. So first we pass it through a phase modulator, and then we generate the FM signal. The question is, how can we incorporate the phase modulation? So this block here, phase modulator, how can we incorporate this phase modulator in practical system? So this is the illustration of this phase modulator. If you recall the approximate waveform of narrowband phase modulator, you can see that this can be implemented by this relationship: xct is equal to AC cos omega ct minus AC phi delta xt sin omega ct. So this is the mathematical relationship that we use, that we have previously discussed regarding the phase modulated waveform. The same relationship is implemented in the systems like this. You can see that first we need to multiply this phi delta with xt. So this xt is weighted by the maximum phase deviation what we need. Then we multiply this with this sin omega ct act. So it is multiplied by sin omega ct ac, which is the phase shifted version of carrier, which is a cos omega ct. A cos omega ct is the carrier, and we have applied the phase shift in order to get the sine function, and we multiply this xt with the sine and then add them together in order to get this phase modulated waveform. So this is the block diagram of the system that we incorporate to implement the phase modulator in a system, and you can see that this requires this operation of addition and operation of multiplication, which can be easily obtained as we have previously discussed in case of amplitude modulation. So this is how we incorporate the phase modulator, and then we pass it through this entire system in order to get the FM output for overall system. And of course, if you want to get the phase modulation, so we do not need to use this circuitry. So this system will directly give you a phase modulated output. Now let us move on to the detection. Of course, at the receiver side, we need to have detection of the signals which are achieved from the transmission coming from FM waveform. So there are a variety of different schemes that can be incorporated in order to detect the FM wave. So few commonly used schemes are mentioned here. First, FM can be detected by using an FM to AM conversion. Second, a phase discriminator, or sometimes called quadrature detector, is also used to detect the FM waveform. A phase lock loop can also be used to detect FM signal, and we sometimes use synchronous detectors to detect the FM waveform. So FM can be demodulated or detected by any of these schemes. So let us quickly discuss each of these schemes individually. So let me start with this division of basic waveform expressions for the exponential modulation scheme. The exponential modulation scheme is represented like this. AC cos omega ct plus phi t, where phi t contains the information depending on the modulation scheme. For PM, phi t is actually directly proportional to xt. For FM, this phi t is actually related to the integral of xt, or message signal. So both of them, they contain message information but with different form. And from here you should see that if we differentiate this phi t for FM, if we differentiate phi t, you would see that this becomes 2 pi f delta into xt, which is actually directly proportional to the xt. So in order to extract the information from FM signal, we can simply detect the phase and differentiate it in order to get the message signal. So this is one of the important point. So detection of phase and phase modulation and FM, they become similar with this perspective, because if we have detected the phase, we can pass it through a differentiator to get the message signal in case of FM as well. So let us start discussing this FM to AM conversion. So what is FM? How can we convert FM to AM signal? So consider this: you have an FM signal. You can see that the amplitude is constant and the frequency is changing as the message is changing. So this is actually FM waveform here. The instantaneous angle would be given by this relationship: phi ct is equal to omega ct plus 2 pi f delta integral of xt. So the waveform is represented by this expression. If I ask you to differentiate this waveform, what should you get? You should get this derivative of xct, and of course derivative of cos is sine theta, but we know that by chain rule of differentiation, the derivative of this theta should be multiplied. So you can see that I have multiplied the derivative of theta here. So if we calculate the derivative, what you should see, that because theta is given by this expression here, if we differentiate, so it will give you this value 2 pi fc plus f delta xt. So you can see that if I substitute the value of derivative of this theta here, you can see that this will appear in the product of this sinusoidal function. You can notice that this is a sinusoidal function whose amplitude is dependent on xt. Now this xt becomes the part of amplitude. So this is the time domain amplitude, or envelope. And you should realize that this is the same form that we have for AM case. In AM, the message signal appears in the envelope of the sinusoidal carrier, and this is the same form where you have a sinusoidal function and envelope which is dependent on xt. So you can simply see that if we differentiate FM signal, it converts it to the AM waveform. So in order to convert an FM signal to AM, what we need to do, we need to perform a differentiation operator, operation which can be obtained by a variety of different circuits. So if we have a FM waveform, so what we do, first we pass it through a limiter circuit, as we have previously discussed that it is used to remove the noise spikes from the system, and then we pass it through a derivative circuit. So once we get the derivative, so this FM which is available here, it gets converted into AM waveform, which would be available at this point. So AM can be detected in similar way as we have previously discussed, and you should recall that use envelope detectors to detect the AM waveform. So this AM signal can now be detected by a simple envelope detector, and sometimes we need to use a DC blocking component, so that if there is any DC component, that is removed from the signal. You should notice that this entire setup does not require any synchronization. So whatever FM waveform is received, it can be easily detected by converting it into AM signal by differentiation operation, and then using an envelope detector to detect the message signal. So this scheme is actually a non-coherent detection of FM signal. So we can use it for non-coherent detection. Second scheme that we use for detection is called phase shift discriminator, or sometimes we call it a quadrature detector. So what is a quadrature detector? In order to understand the principle of this quadrature detector, we need to focus on this network which is illustrated here. Let me give you a simple case. Let's say we have a waveform Vt. So if we find the derivative of Vt, so derivative of Vt would be this by the first principle of derivative, Vt minus some change divided by some change, where this T1 is a very small number. So this is the basic definition of derivative from first principle. So if we have this xct which is represented by this value, and we want to find this f delta, because the derivative of not f delta, the derivative of phi t, which is actually related to f delta and xt. So in order to find out this xt, we need to calculate this derivative of this phase. So derivative of phase would be represented by this expression phi t minus phi t minus t1, that can be approximated as t1 phi 1 t. So in order to calculate the derivative, we need to calculate this difference here, phi t minus t1. So how do you obtain this difference? So what we do, we use a phase shift network which creates a phase shift among the incoming signal. So if incoming signal is cos omega ct plus phi t, so phase shift network creates a shift such that the signal converts to sine, plus it creates an additional small phase shift depending on the time delay t1. So it creates some phase shift. So if at this point, this as multiplication point, you would see that this multiplication point would give you this product term cos omega ct plus phi t into sin omega ct phi naught t plus phi t minus t1. You can see that this is simple product formula of trigonometry. You can use product to sum formula to expand this relationship, and if you use that formula, you would see that there will be a term which is sin phi t minus t1, which will be extracted from this low pass filter, because all other terms would be having higher frequencies, and this term would be having smaller frequencies. So this is generated by this low pass filter, sin phi t minus phi t1t. And we know that for smaller angles sin theta can be approximated as theta, so this sin theta can be approximated as this phi t minus t1t. So this value t1 phi dot t, which is derivative of phi t, is actually given by this expression. So this t1 phi dot t is obtained from this network here, which is actually directly proportional to the xt. So whatever you get at this end is actually directly proportional to the xt, and by dividing the function by that proportionality constant, we can easily calculate the value of xt from this phase shift discriminator. The third scheme to find out, so to demodulate the exponential wave modulation schemes, including both phase modulation and frequency modulation, is by using synchronous detectors. So how can we use synchronous detectors here? We know that the modulated waveform is represented by this expression here, AC cos omega ct plus phi t. If you expand it, so you can expand it into two terms. One is the I component and one is the Q component, as we have previously discussed. The I component is AC cos phi t, whereas the Q component is AC sin phi t. So actually this modulated waveform, it has two components, I and Q component. The synchronous detectors, they actually detect these I and Q components. By I and Q component, you should realize that these I and Q components are actually cosine and sine components. So you have to use the synchronous detection procedure that we previously discussed in AM case in order to detect this I component and Q component. Let me quickly bring up the synchronous detection case that we. Okay, notice that this is a synchronous detection case that we discussed previously when we were talking about the AM scheme. You should notice that in order to do this synchronous detection, we need two operations. One is this multiplication of the message signal with the local oscillator signal, and then we use low pass filtering. And we have previously discussed that if you multiply this local oscillator with cos omega ct, in that case it becomes cos square omega ct, which generates two terms. One is the message signal and other is the high frequency term, and this high frequency term can easily be removed by using low pass filtering. So if we use low pass filtering, so we will end up with the required component only. So basically what we need to do is whenever we need to have a synchronous detection, we need to multiply the signal with the local copy of the oscillator, and then we have to pass it through the low pass filtering. Coming back to our case here, what we were discussing about the synchronous detection of the FM signal, you should see that we have two components. One is the I component and Q component. So we need two synchronous detectors here, one for detection of I component or cosine component and another for Q component or sine component. So how we implement this? So for I component, we have to multiply the signal with cos omega ct and pass it through low pass filtering in order to find this I component of the signal. And in order to find Q component, you have to multiply the signal with sine omega ct and then pass it through low pass filter in order to get the Q component in the signal. So you can see that we can by using two synchronous detectors, actually we can easily find out what is the I and Q component in the system. Once you have I and Q component, you can see that you can simply divide these two in order to see that this phi t can be calculated by simple mathematical operation of tangent inverse. So if you take the tangent inverse of ratio of Q component and I component, so if you divide these two and get the tangent inverse, you would see that this will result in the phase of the signal. So in order to find out the phase, you should calculate this arc tangent operation of Q upon A, which gives you the phase of the signal. And you can see that the phase, actually for PM, this is actually representing the information signal, because the information is directly related to the phase of the message signal. However, if you are using the FM for transmission, in that case you have to pass it through a differentiator in order to get the message signal from that phase information that we got from the synchronous detector at the previous stage. So you can see that this entire setup can be used for both PM as well as FM. The only difference is this differentiation operation. For FM, for PM, of course the output of this synchronous detector would give you the phase directly, whereas for PM the output would give you the phase information directly, so that you can get the message signal from that phase information. However, for FM, we know that as the phase is related to integral of in FM, integral of the message signal in FM case, so in order to get the message information, you have to differentiate whatever phase is received, and after differentiation you will get the information signal back in case of FM. So this is the third scheme that we use to detect FM and PM by using the synchronous detectors in the system. The last scheme that we use is through the phase locked loop. Actually, phase locked loop is a specialized circuit in communication systems which has many different applications. Actually, this circuit is used for frequency demodulation as well as frequency synthesis and various filtering and signal processing applications. So this is not the specific circuit for the frequency demodulation, rather it has an application in variety of different areas. So what is the phase lock loop? Actually, this is a phase sensitive feedback loop which actually generates the frequency and phase in accordance with some incoming signal. So actually it has three different components. One is called phase detector. So we have a phase detector which is actually compares the phase which is obtained from incoming signal and whatever signal is coming from the VCO. So there are two signals. One is the voltage controlled oscillator which actually generates a sinusoidal signal, and one is the incoming signal which is in form of FM. So it will see if there is a phase difference between those two. So if there is no phase difference, it will generate zero signal here, but if there is some phase difference, so it will generate a positive or negative signal depending on the phase of phase difference between these two signals. The signal which is generated here is through a low pass filter in order to get a DC signal at the output, a constant value depending on whatever the phase difference is obtained at this stage. This signal is called error signal. Actually, this error signal is related to the phase difference between these two signals. So this error signal is actually fed back to the VCO which actually generate a sinusoidal signal depending on this VCO. So say for example, if this FM signal has incoming FM signal has a higher frequency compared to this VCO signal, so this phase would phase detector would generate a signal, positive signal. So eventually you would be having a low pass, you will be having a positive signal at this low pass filter. So this positive signal will force VCO to increase its frequency. So once its frequency is increased, so eventually the VCO and FM frequency would becomes same. So as soon as the frequencies becomes equal, so the signal would be a zero signal will be available here. So there is no further correction needed. So VCO and FM would be having the same signals. So eventually you can see that this VCO is actually will be following whatever FM signal is coming at the input side, and of course this signal out of this low pass filter is actually representing the variation. So whenever the FM frequency changes, so eventually this variation would appear at this stage. So if frequency increases, you would see a positive signal here. If frequency is decreased, you would see a negative signal here. So that is what the message signal should look like. As the message signal increases, so FM frequency increases. So this is, you can say, this circuit is making the reverse of that process. So whenever the frequency is increasing, you would see an increased signal here. That means increased message signal here. Whenever FM frequency decreases, so you would see a decreased message signal here. So this point here is actually represents the recovered modulating signal. So at this stage you would be having the modulated signal here. So whatever I tried to explain here is also listed at in the next slide for your convenience. So you can see that the phase detector has two input signals, and it compares the two signals in order to generate output signal. That output signal is used to control the VCO. If there is a phase or frequency difference between FM input and VCO signal, the phase detector output will vary in proportion to the difference, and eventually it will force the VCO to change its frequency in order to follow the incoming signal. So eventually this error signal actually which is generated from this low pass filtering, it actually follows the message signal, so it can be used to detect whatever message signal was there. So these are the four different methods that we use for demodulation of FM as well as PM signals in our systems. So concluding today's discussion, we have discussed different circuits and different techniques that we use for transmission of FM signal as well as the demodulation or reception of FM and PM signal. So this is all for today's lecture. Thank you all.